Welcome to This Explainer. Today, we're diving straight into the nuts and bolts of how data actually finds its way across the massive, tangled web we call the internet. We all kind of take it for granted when a web page loads, right? But the invisible infrastructure making it happen is absolutely fascinating. So we're going to take a deep dive into one of the foundational protocols that literally made early networking possible, the Routing Information Protocol, or as we all know it, RIP.
Okay, real quick, here's our roadmap for today. We'll start with a routing dilemma, meet RIP and its distance vector logic, break down the fatal routing loop, look at our engineers fix those nasty flaws, and finally, wrap up with RIP's modern-day legacy. Let's get into it.
Part 1. The Routing Dilemma, Moving Beyond Manual Configuration. To really appreciate the brilliance of automated networking, we've first got to establish the exact problem we're actually trying to solve here.
Imagine having to give a friend turn-by-turn directions across the entire country, but you have to write down literally every single intersection on a piece of paper. That is basically static routing. It's got a massive management cost because you're manually configuring every single device. And the worst part, if a road suddenly closes, your instructions are completely useless. It doesn't adapt. We need data to navigate complex networks on the fly, which is exactly why dynamic routing was born. It lets routers automatically calculate, update, and sync their paths, instantly adapting to topology changes without us having to babysit them.
Now, before we look at how routers actually talk to each other, let's peek inside a single router's brain to see this input-to-output pipeline. When a router gets an IP packet, it's not just guessing. It immediately opens up its internal dictionary, the routing table, to find the absolute best match for that destination IP. Once it nails down that match, it just follows the instructions and punts the packet to the correct next hop or exit interface. At its core, it's just a beautifully simple matching game.
All right, moving to Section 2. Meet RIP, the distance vector, or as I like to call it, the hearsay protocol. Now that we know why dynamic routing is a must, let's formally introduce our main character. So, in the grand family tree of networking protocols, RIP sits right inside the internal gateway protocols, or IGPs, the guys managing traffic inside a single organization. More specifically, RIP is a distance vector protocol. This is super different from the other major branch, link state protocols like OSPF, which actually build out a complete mathematical map of the entire network. RIP definitely doesn't do that. Which brings us to its most defining and honestly kind of quirky characteristic.
RIP runs entirely on hearsay, or blind navigation. Seriously, a distance vector router operates completely in the dark. It only knows two things: the distance to a destination measured in hops, so basically how many routers it has to cross, and the direction, meaning which literal cable to send the data down. It is completely blind to the global network map. It purely relies on what its direct, physically connected neighbors tell it. If router B tells router A, hey man, I can reach that destination in 2 hops, router A just blindly believes it, no questions asked.
To see this hearsay in action, let's look at time t0, the exact moment you power the routers on. Right now, routers R1, R2, and R3 are just isolated little islands. They only know about the networks physically plugged directly into them. R1 knows its left and right cables, R2 knows its own, and so on. Their routing tables are essentially totally blank outside of their immediate physical surroundings.
Fast forward to time 10, the steady state. Now they've started talking. R1 tells R2 what it knows. R2 adds a hop to that distance and passes the gossip down to R3. They learn these routes from each other, hop by hop, until the whole network reaches a fully converged, steady state. Every single router now has a complete list of destinations and the best direction to forward data, all built 100% on the word of mouth of their neighbors.
Which brings us to Section 3, the fatal routing loop, a critical system failure. Look, hearsay sounds great in theory, right? It's simple, it's effective, low maintenance, but because RIP relies entirely on this neighborly gossip, it harbors a massive and, frankly, fatal vulnerability.
Let's break down the worst-case scenario. Say a connection suddenly goes down. A router needs a second to realize it and tell its neighbor. But what if there's a slight delay? Let's say R1 loses its connection. Before R1 can warn R2 that the network is dead, R2 sends its regular update saying, hey, I have a path to that network. R1, being totally blind, believes R2 and updates its table to route through R2. But here's the catch. R2's path was actually going through R1 in the first place. This slight delay creates a disastrous infinite loop. R1 sends the packet to R2, R2 sends it right back to R1, and suddenly you've got bad data bouncing back and forth at the speed of light.
As you can probably guess, an endless routing loop is a catastrophic system failure. It eats up all your bandwidth, router processors completely max out, and the network just crashes. So how on earth did engineers solve this critical flaw?
Let's find out in Section 4, Fixing the Flaws, Engineering Clever Workarounds. To save RIP from its own blind spots, networking engineers had to invent some incredibly brilliant, if maybe slightly clunky mechanisms to forcefully break the loop.
The first big fix is called split horizon. Think of this as a logical firewall against circular logic. It enforces one super strict, unbreakable rule. If you learned a route from a specific interface, you never ever advertise that same route back out of that same interface. So if R2 learned about a network from R1, it'll happily share that info with R3, but it completely censors that detail when talking back to R1. This one simple rule stops that two-node ping-pong effect dead in its tracks.
And then we have the second major fix, route poisoning. Remember how RIP measures everything in hops? Well, it has a hard limit. 15 hops is the absolute maximum. So when a route suddenly dies, the router immediately marks its metric as 16 hops. In RIP speak, 16 literally means unreachable, or infinity. Instead of just quietly deleting the route, the router actively spreads this poisoned 16-hop route to all its neighbors. It essentially forces every router on the network to instantly flush the dead path, overwriting any lingering bad hearsay, rather than waiting around for regular updates.
But beyond just preventing loops, the protocol itself actually had to evolve to keep up with the internet. RIP version 1 was incredibly basic, but version 2 finally brought in some vital features. The biggest game changer was support for variable length subnet masks, or VLSM. Basically, RIPv1 assumed all networks were just default standard sizes. RIPv2 finally let routers share exact subnet masks, making routing vastly more efficient. It also layered in security through authentication to block rogue routers from injecting fake routes, and added route tags and nexthop info to finally shake off version 1's archaic limitations.
But hey, even with version 2, you still got to be super careful. One of its default features is automatic route summarization at classful network borders. Essentially, to save memory, it tries to bundle multiple small networks into one giant advertisement. But if you have two physically separated networks that happen to share the same major address block, RIP will automatically summarize them at the border. This accidentally creates equal cost load balancing errors. The router gets completely confused, thinks the destination is in two totally different directions, and effectively drops your packets into a black hole. Modern engineers almost always have to manually disable this auto-summary feature just to avoid a disaster.
Which brings us to our final part, Section 5, RIP's modern legacy. Where does it fit today? So, after decades of patches, loop preventions, and protocol evolutions, what's the objective, bottom-line verdict on RIP in today's networking landscape? Here are your 3 core takeaways. Rule 1. The hard 15-hop limit. If your destination is 16 routers away, RIP literally cannot reach it. It is built exclusively for small, flat networks. Rule 2. Its blind hearsay algorithm is heavily flawed. It converges slowly and is naturally prone to those deadly loops, meaning you constantly need split horizon and poisoning just to keep it alive. And Rule 3. Because of these limits, it is virtually obsolete in massive enterprise networks, replaced entirely by heavy hitters like OSPF and BGP. However, because its configuration cost is practically zero, it remains an absolutely perfect teaching tool and a reliable survivor for small, edge networks where you just need something fast, simple, and ready to go. Which leaves us with one final thought to ponder. As our global internet infrastructure gets infinitely more complex, demanding lightning-fast convergence and unbelievable scale, are we eventually going to engineer out these simple, crude protocols entirely? Or is there a foundational truth here that no matter how gigantic the system gets, simplicity and ease of use are exactly what keep the quiet edges of our networks alive? Thanks for joining me on this explainer today. I hope it helped illuminate some of those invisible pathways making our digital world tick.